This video is for section 4.6, graphs of other trig functions. In the previous lesson, we graphed sine and cosine. In this lesson, we will be graphing secant, cosecant, tangent, and cotangent. In order to successfully graph secant and cosecant, it's important that you have a firm grasp on graphing sine and cosine. So if you do not feel comfortable graphing sine and cosine just yet, you may want to hold off on this lesson. As mentioned, in order to graph cosecant and secant, we are going to use the reciprocal function as a reference. Remember, the reciprocal of cosecant is sine, and the reciprocal of secant is cosine. So let's start off with the graph of cosecant. So there are a couple things that we want to talk about. So again, we know that cosecant is the reciprocal of sine. So what I can do is I can rewrite cosecant as 1 over sine. And 1 over sine, we know that this fraction is undefined when sine of x is equal to 0. Because if this denominator here is equal to 0, then cosecant will be undefined. And we know that sine is equal to 0 here and here on the unit circle. So at 0, pi, 2 pi, 3 pi, so on and so forth. So whenever sine of x is equal to 0, cosecant of x will have a vertical asymptote. And this is very important. So again, wherever sine of x is equal to 0, there will be a vertical asymptote in the graph of cosecant. The vertical asymptotes will occur at any multiple of pi, and that's what this notation is. This is just saying any multiple of pi. So as we did previously, here's a little chart. And if we know sine of x, we can find cosecant by taking the reciprocal. So on and so forth. So if I were to plot these points, we would get something like this. Now this is important, and here's why. The first thing we're going to do in this case is we would graph sine, because sine is the reciprocal of cosecant. So this dashed line here is the graph of sine of x. Wherever sine of x touches the baseline, a vertical asymptote will occur, and that's what's marked in red. Additionally, wherever sine of x had a maximum or minimum will be the opposite of that in the cosecant function. So basically, when you graph these, you'll first graph sine of x lightly, and then you'll draw in the asymptotes. And then wherever a maximum or minimum occurs, you'll just have these little branches. So one full period is a branch that opens upward and a branch that opens downward. So here, the period again is 2 pi. The graph of secant is basically the opposite. So we know that cosine is the reciprocal of secant. So whenever cosine of x is equal to 0, secant of x will be undefined, and there will be a vertical asymptote there. We know that cosine of x is equal to 0 here and here. So at pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, so on and so forth. So any odd multiple of pi over 2 is where vertical asymptotes will occur for the secant graph. Here we just have a chart like we did before. If we plot these points, we end up with this. So again, what we'll do is we'll graph cosine. Wherever cosine touches the baseline or the x-axis, that's where the asymptotes will occur for the graph of the secant function. And then wherever the maximums and minimums occur, that's where the maximum or minimum of the little branch will be. Okay, so this is why it's important to know how to graph sine and cosine. Now here, this is all the information about cosecant and secant. It involves the domain, the range, amplitude, period, vertical asymptote, symmetry. You can pause the video and take a little look-see at that if you want. But I'm going to just jump into graphing these right away. So here I want to graph -2 cosecant of 3x. So the first thing we want to do is first we want to graph the reciprocal function, which would be -2 sine of 3x. If I can graph this, then I should be able to graph the other part, which is the cosecant graph. So let's review this. I can see that I'm going to have a reflection across the x-axis. I can also see that my amplitude is 2, and I also know that my period is going to be 2 pi over 3. I don't have a vertical shift or a horizontal shift or a phase shift, so I can go ahead and sketch this graph of sine now. So when I graph this, I know that the x-axis is going to be my baseline. Oh, one thing I might want to do, well, remember we can sandwich the argument in between 0 and 2 pi, then divide by 3, and we'll just discover that x is in between 0 and 2 pi over 3. Okay, so I know that one period is going to end at 2 pi over 3 on the sine graph. So let's see. When I graph this, half of 2 pi over 3 is pi over 3. Half of pi over 3 is pi over 6. So I have 1 pi over 6, 2 pi over 6, 3 pi over 6, and 2 pi over, 3 pi over 6, 4 pi over 6 is what we have there. So I'm going to graph sine. So here, here, and here. The amplitude is 2. So, and there's a reflection. So this is the graph of cosecant. And remember, the graph of, sine. Remember, the graph of sine will continue forever and ever and ever in both directions. So now I'm going to graph cosecant. So wherever the sine graph touches the baseline, we will have asymptotes. And then we will graph the cosecant graph at the maximums and minimums. And these will extend forever in both directions. So here is that graph. Okay, let's do another one. Here we have -2 cosecant of 3x plus 1. This is the same as the previous example. The only difference is we have a plus 1. So it's the same as the previous example, but we've shifted everything up 1. So what I've done is I have shifted the baseline, and I'll show you what happens here. So instead of this being the baseline, we have moved it up 1 unit. So the baseline is now here. And if we were to sketch the graph of the sine function, we would start here and here, and then we still have that reflection. So this would be the graph of sine, and then the asymptotes will still occur, not where it crosses the x-axis now, but it's wherever the baseline is. So since we shifted up 1 unit, our asymptotes have changed. Okay. Pause the video and give this one a try. We are going to graph this first as y equals 2 cosine of 4x. Here, we know that the amplitude is 2. The period is 2 pi divided by b, and b is 4, so the period is pi over 2. So to find our starting and ending spot, we will sandwich the argument in between 0 and 2 pi. And we will discover that we will start at 0 because we don't have a phase shift. And we will end at pi over 2. All right, so let's give this a try. So I'm going to end at pi over 2. Half of pi over 2 is pi over 4. Half of pi over 4 is pi over 8. So I have 1 pi over 8, 2 pi over 8, 3 pi over 8, and 4 pi over 8. My amplitude is 2. So I don't have a vertical shift, so I'm not moving my baseline at all. So I can go ahead and graph cosine. Remember, cosine will start and end at its maximum. Halfway between, it's at its minimum, and 1/4 and 3/4 of the way, it's at the baseline. So this is the graph of cosine. And remember, cosine will continue forever and ever in both directions. Since our baseline didn't change, our asymptotes will occur wherever cosine is equal to 0, which are in these spots here. And then my graph of the trig function 2 secant of 4x will really be this piece here. So technically we should erase this blue graph. We would erase all of this. And then what is left is the graph of the secant function. Give this one a try. So here, this is similar to y equals sine of x plus pi minus 2. In this case, I can see that we will have a phase shift and a vertical shift, so we will need to be careful. My amplitude is 1 because I don't have anything in front. My baseline shifts down 2 units, and I will sandwich x plus pi in between 0 and 2 pi. When I solve this, I get negative pi is less than or equal to x is less than or equal to pi. So we'll go ahead and see what we get. So I'm going to start over here at negative pi, and then pi will be over here. So I can see that halfway between is 0. So that's helpful. I do need to shift my baseline. So my baseline will become this. All right, so when I graph the sine graph, I'm going to start at negative pi and end at negative pi and halfway between. This value here is going to be pi over 2 and negative pi over 2. We don't have a reflection, so our points will be here and here because my amplitude is 1. So if I were to graph sine, it would be like this. I'll just graph it solid. And then it just repeats. So my asymptotes will occur wherever the graph touches the new baseline. And sometimes you'll want to write equations for these asymptotes. And then the branches will be here, and here, and here, and here. Oh, sorry, that got a little funny. Okay, and there you have it. Okay, so that basically wraps up what I wanted to tell you about graphing secant and cosecant. So now we're going to jump into graphs of tangent and cotangent, starting with tangent. And I want to remind you that tangent is written as sine of x over cosine of x. So a couple special things happen. Remember, whenever a fraction has the top equal to 0, or whenever a fraction equals 0, in this case the top has to be 0, that means that we will have an x-intercept wherever sine of x is equal to 0. Whenever cosine of x is equal to 0, so this gives us an x-intercept. This gives us a vertical asymptote. So we've already talked about when sine of x is equal to 0, sine of x is equal to 0 at multiples of pi. And we've talked about when cosine of x is equal to 0, which are multiples, odd multiples of pi over 2. Okay, so again, this will be helpful. Some more important information about the tangent graph is that the tangent function is an odd function, so it will be symmetric with respect to the origin. Odd, symmetric about the origin, and that's really an algebra topic, so you should be somewhat familiar with that. Then one big difference is that the tangent graph and the cotangent graph, they each have periods of pi. So since they have periods of pi, that is one thing that is very different than the other graphs. So let's take a look at what this graph actually looks like. As you can see here, this graph is different than the rest that we've seen. Pardon my puppy, she's naughty. At first glance, hopefully you can see how this graph is different than the others. So again, remember tangent of x is equal to sine of x over cosine of x. So whenever cosine of x is equal to 0, we will have an asymptote in the graph. And so that occurs at odd multiples of pi over 2. And then we will have zeros on the graph whenever sine of x is equal to 0. So this will be an x-intercept. So the x-intercepts occur at multiples of pi. And then the sine graph, it kind of looks like an S a little bit, a snake, a curve. And one full revolution, or not a revolution, but one full cycle takes place over pi units. Let's talk about the cotangent function now. It is the same thing, but the reciprocal. So now whenever sine of x is equal to 0, we will have an asymptote. Whenever cosine of x is equal to 0, we will have an x-intercept. So things that we have already talked about. So again, cosine of x is equal to 0 here and here. It's odd multiples of pi over 2. Sine of x is equal to 0 here and here, multiples of pi. So, a couple more things. Cotangent is also an odd function, so it is also symmetric with respect to the origin. The period is pi. The thing that's different, the tangent graph takes on this shape. Cotangent is, cotangent is just the opposite direction. So here's the graph. And again, your reminder, cotangent of x is cosine of x over sine of x. So whenever sine of x is equal to 0, you will have asymptotes, and that's why there are asymptotes at multiples of pi. Okay, so just like the secant and cosecant graphs, here's a little chart that illustrates information about tangent and cotangent. You're welcome to pause the video and take a look at that if you want. This slide basically talks about some important aspects of graphing tangent and cotangent. And I think students get the hang of it once they dive into it and start working with it. But we will still have a scaling factor. We will still have shifts, so a vertical shift and phase shift. One thing that's different is when we want to find the period, instead of taking 2 pi divided by b, we take pi divided by b. So this is one big difference that you'll see. Another difference that you'll see is the approach in which we graph. There's really a bit less involved when graphing tangent and cotangent, which is nice. So one thing that you'll want to pay attention to is basically you can identify where the asymptotes occur. And the asymptotes will occur for tangent on multiples of pi over 2. So when we were graphing sine and cosine, we would sandwich the argument between 0 and 2 pi. But for tangent, we are going to sandwich the argument in between negative pi over 2 and pi over 2. These are just the smallest values in which the asymptotes occur. So they're just 2 consecutive asymptotes. Okay, so you'll want to remember this. Now, when graphing cotangent, our 2 consecutive asymptotes in this case will be 0 and pi. Okay, so these are things that you'll want to pay attention to. So the first step when graphing tangent and cotangent is to find two consecutive vertical asymptotes, and this is how you will do it. The next step, what you'll want to do is you'll want to plot an x-intercept halfway between the two asymptotes that you found in the previous problem. And then you'll just sketch the general shape of the parent function. I'm not worried about any more accuracy than this. We're just going to keep it simple as long as you know the basic shape that the graph takes. Okay, so basically the rest of the video is just me showing you different examples of how to do this. Oh, I'll show you examples. Okay, so the first one is cotangent of 4x. So the first thing I want to do is figure out a cycle. So for one cycle, since this is cotangent, I'm going to sandwich my argument in between 0 and pi. Now notice that my inequality symbols do not include the values. It's just less than and not less than or equal to. That is because that's where the asymptotes occur. If I divide by 4, I have this. So my two consecutive asymptotes will be at 0 and pi over 4. So here's pi over 4. If I double pi over 4, I get pi over 2, so there will be an asymptote there as well. And I can also go in the negative direction, so negative pi over 4 will also be an asymptote. Then step 2 is to identify the halfway point. In this case, it would be pi over 8. This is 1 pi over 8, 2 pi over 8. So 1 pi over 8, 2 pi over 8, 3 pi over 8, 4 pi over 8. So cotangent takes on this shape. So my graph will look like this. This is 1 period, 2 periods, and I can also go in the opposite direction as well. And here's the computerized graph. Not so bad. Next example is tangent. Remember, the graph of tangent takes this shape here. I will want to find my consecutive asymptotes, so I'll be interested in finding one cycle. For tangent, I sandwich this between negative pi over 2 and pi over 2, and again, the endpoints are not included. I'll subtract pi over 3 from both sides. When I do, this is negative 5 pi over 6, and this is pi over 6. Divide by 2 is the same thing as multiplying by 1/12. So this is negative 5 pi over 12 and pi over 12. Okay, so that's where my asymptotes will occur, and I'm just going to pull this graph up to kind of show you. So my asymptotes are going to occur at negative 5 pi over 12 and pi over 12. So if I add, let's see here. Sometimes students want to make another cycle and they have trouble figuring out where the next consecutive asymptote goes. So basically, if you have an asymptote here, you're going to add another period. So remember, when we have the graph of the tangent function, the period is pi divided by b, so the period is a half. So to get from pi over 12 to the next asymptote, I will add pi over 2. And so you might want to rewrite this as 6 pi over 12. 6 pi over 12 plus pi over 12 gives us 7 pi over 12. Okay. Now we may also have trouble coming up with the middle point. So remember, really what we're just doing here is we're finding the average between the asymptotes. So to find the midpoint, I'm just going to take the average. I'm going to take negative 5 pi over 12 plus pi over 12 and divide by 2. So this gives me a negative 4 pi over 12 divided by 2, which is negative 4 pi over 24, which is negative pi over 6. So that's where the middle point will be. And then tangent, remember, increases from left to right. Here's one we haven't seen before, and that is when we have a reflection. So if tangent is negative, remember the basic parent function of the tangent graph goes upward from left to right. Well, we're reflecting this across the x-axis. So the upper portion comes down here, and then the lower portion comes up here. So it really kind of takes on the shape of a cotangent graph. So the negative out in front causes this tangent graph to look like a cotangent graph. So let's identify one cycle. Remember, with tangent, we sandwich the argument in between negative pi over 2 and pi over 2. Now, one thing I'd like to point out is we do not have any parentheses here. Since I don't have parentheses here, it is assumed that only 3 pi over 4x is the argument. Okay, so this is telling me that I'm going to have a vertical shift up 2 units. Okay, so we're only sandwiching 3 pi over 4 then. So I multiply all sides by 4 over 3 pi. And when I do, I end up with negative 2/3 is less than x is less than 2/3. So this one's a little bit different. We end up with no pi's, all the pi's cancel. And this is what we end up with. So again, our baseline shifts up 2 units. Our asymptotes occur at negative 2 pi over 3 and, I'm sorry, negative 2/3 and positive 2/3. And then our reflection makes it look kind of like a cotangent graph. And there you have it. Here is the last example that I'll do involving tangent and cotangent. Go ahead and pause this video and give this graph a try. So we're dealing with cotangent here. This tells us that our baseline shifts down 3 units. We also have a phase shift here because I'm adding something in the argument. So remember, with cosine, we are going to sandwich the argument between 0 and pi. I'm going to subtract I'm going to subtract pi over 2 from all sides. So my first asymptote will be at negative pi over 2, and the other one will be at positive pi over 2. So call this negative pi over 2. Here is pi over 2. So I know I have asymptotes there and there. And then in the middle, I know that cotangent takes on not that shape, but this one. So it will look like this. All right. If you want to do another one, it will occur at 3 pi over 2. And this will be pi. And it'll look like this. And there's a nice short video for you for this section 4-6.